So, hearty welcome to everyone. I won't say it for a third time. So, this is a special symposium because of the participation of IITB. So, thanks to everyone who has come here to give talks. Looking forward to all of them. And going by the weather, it looks like we were a bit unlucky in our choice of dates, but we've been super lucky in having Chiranjib, Neeldhara, and Bharat as our keynote speakers. Thanks so much for coming all the way here. Finally, this is an event to showcase our talent, the STCS talent. Looking forward to the talks of all STCS students and postdocs. And it wouldn't have been possible without the efforts of Jatin, Raghuvansh, and our office staff. So, and you know,
Thanks, Kavita. Welcome, everyone. Good morning. So we're very happy to have Professor Chiranjib Bhattacharyya from the Department of CSA, Computer Science and Automation, IISC, who is known to many of us here. His interests are in foundations of machine learning, optimization, and applications to industrial problems. He's a fellow of the Indian Academy of Engineering, Indian Academy of Sciences, and the Asia Pacific Artificial Intelligence Association. So he joined the CSA IISc in 2002. Prior to that, he was a postdoctoral researcher at UC Berkeley. And then before that, he received a PhD from the same department, I believe, CSA. And he has a master's from IISc itself, and also from Jadavpur, where he did his bachelor's. So with that, let me welcome Chiranjib.
So good morning, all of you. It's a pleasure to be here. Thanks to Raghuvansh and Jatin for inviting me. Thanks, Kavita, for this kind introduction. Thanks, Vinod. So, when Raghuvansh invited me, I sent in an abstract. And at that point, I was in a hurry, so that was the latest abstract I had. I sent it. And then after that, yesterday night, I was checking the website and what this program is all about. And then I thought I'll change the title. And so title is changed after. So the talk will not go as planned, as you have written abstract. It will be something else, but related. So what is it? So it's a fancy mouthful: latent variable models, model surgery, and quantum EM. So basically, these are vignettes of my research themes. So as usual, in the morning, it's not a good idea to bore people with all kinds of details. So what I'll do is, I will give you some glimpses of interesting things which I think I'm doing. And then if there is interest, we can talk in the breaks and things like that. So, agenda is basically three things. What is called learning latent variable models. Now, all of you are aware of this Gen AI, generative AI. So generative AI started with these kind of formalisms. And then we'll motivate what model surgery means. And then lastly, we'll talk about my recent developments, which we have been involved in developing algorithms in the quantum computing setting for learning latent variable models. But by and large, what I wanted to talk about is, this is a talk I never gave to anyone, because the audiences which I go to are mainly machine learning community. So here I thought is a nice theory community. So the last 2 decades, I had an absolute blast, in interacting with quote unquote real theorists, and how that intersection has enriched me, especially in the field of machine learning. Yeah, but before that, I want to share couple of interesting problems, and I'd like you to keep these problems in mind, and hopefully the need for theory will be even more. when we talk about this. So one of these is this. So I'm not sure how many of you know these things because the theory community, right? So have you seen these things? Any of you? Just to talk interactive. These are names of some models, right? And now this is a little dated paper. Now, so somebody has measured the energy consumption of these models when you run one iteration of training this algorithms. One iteration. So in IISc, just to reflect this, in IISc, for example, when we push our students, so deadline coming, give it result, this, that, right? Sometimes they say, the room is getting hot. GPUs, right? So these are some of these things, right? So these numbers don't make too much of a sense unless you give them some context to it. So here is the context. So maybe you should compare this. So air travel between New York and San Francisco this is CO2e. So what is CO2e? This is carbon dioxide equivalent. So this is the energy we spend. The CO2 equivalent is this. How do you compute this? In many places. So today's electric lights are on, right? Now we can ask how much of this power came from coal, how much of this power came from wind energy. So these mixes are available in many places. I'm not sure in India though. So from that, you can get an approximate number, which is called CO2 equivalent, meaning this amount of coal you have burned. Now I just wanted to compare these numbers. This is this, and this is this. One back and so basically you're burning as much as carbon dioxide by one iteration of bird between New York and San Francisco. What is even more alarming is this transformer model, right? This is by the way a little dated. Now this has gone to billions. One iteration is something like this, right? CO2 equivalent is something like this, right? I have no idea what those things. You can divide it up. Okay, let's forget the car. Okay, so let's take this number. This is an average good car in San Francisco or US. This is the CO2 equivalent. And look at this. 5 times that. Let's assume similar things. Now, a technology which is touted as will change civilization. And all of us want it. All of us want ChatGPTs and things like that. All nations are trying to build their own things. Companies are going to build this thing. Okay? And these are, as you can see now, this number has gone to billions now, billion number of parameters. And obviously, more number you multiply, this number is going to go up. So obviously now this kind of technology is not sustainable, right? And if you, I'm not making this up, if you want to look in this paper, and there are lots of very interesting observations like this. So basically, the main thing is carbon footprint of DNN models, deep neural network models, is completely unsustainable. It is too high, right? So second is another thing is, so one of my favorite actors, Scarlett Johansson, right? You see, she was in news. One of these news is, you can check this up. She and others are all suing AI companies, like because ChatGPT and other things, have the voice thing, right? It appears that as if she is speaking. And now she says, no, and it appears, it could appear that she's endorsing a product. The generative AI voice you hear, right? The voice, sometimes when you start using this, you see a voice, right? The voice is some person, like, it's not a person's thing, but somebody might say it's like, looks like my voice. And now these kind of lawsuits are cropping up. Because when these models were built, how do you build such a model? You just scrape the internet where if you have the capacity, and then you train your models. At that point, there are no laws, no regulations. Academics work like that because we never intended to for commercial use. Whatever you scrape the data from wherever, build your models. But now these are industrial scale models. There are business involved in it, lots of other ramifications. And now lawsuits are coming up, and more such lawsuits are going to come. So how do you handle this kind of problems? So this is like 2 problems I want to keep in mind. And model surgery is one of the ways to handle this. So we'll talk about that. Okay. But then coming back to my earlier point, right? So, so as I said in the last, so what I'll do is I will showcase some results, my personal research results, where I greatly benefited from interacting with CS theory. So basically, one of the ways, a bridge between like the so-called CS theory and so-called machine learning scientists is this problem of large-scale optimization. Where in machine learning, what we have is, we have to train models, as you saw some of the numbers, from large-scale data, right? And now there are several interesting tools CS theory has developed, for example, randomized algorithms, high-dimensional geometry, and many other things, which I think can have a huge impact on this, right? Now, sometimes also the development I also feel, so the idea is, oh, you're ML guy, okay, I'm a theory, now you take our method and apply, which is fine. But also, interaction also, I'll show you that we can also pose very interesting new problems, which are of interest to the theory community alone. And I will showcase some of those things as well, right? So this shows there's a very nice, unique, space that can emerge between interaction between these two things, right? Okay, now getting to this, right? So it's a bit of history. Now this support vector machines is historical now. Nobody cares about this. It's, but I think still for the points I wish to make, I want to recall this model. Like, go back 15 years ago, this would have been the hottest topic then. Okay, so this problem is very simple if you strip away the statistics of it. So essentially, I'm given data points, xi's are vectors and yi's are some labels like ones and minus ones. And you are asked that given an x, can you predict y? So this is a prediction function, right? That means I need to figure out w and b. These are unknown things. And the way you do it is, and you want to predict that if I put xi here, I must get y. Right now, those constraints are put in form of constraints like this, linear inequalities like this, and objective is something like this. Right now, this is so now the reason for the objective is a much more larger philosophy at play, where you trade off model fitting with model complexity. So half norm W square, so notion of model complexity, right? And why is it a good thing to keep the complexity low? For example, higher, if higher norm is higher complexity, then what is the rationale for this? Now, there are many theories for statistical theories for this. One thing is that it gives you better generalizability. That's an unseen data you may do well if you pick a simpler model. Okay, all this 30-second spiel. Now, yes. If you scale W and V down, you won't be able to match this one. 0 is right. That is the interesting. But anyway, so as you see, this is a very simple problem. Like this is 1990, 2000. Oh, in 1960, I solved this problem. What are you talking about? Okay. I give you a problem, data, code doesn't run. Because now n is like, I can put 1 million examples just like that. And there are no working code for solving these problems. And that created this new buzz, in optimization. Now you'll see many optimization researchers want to write papers in machine learning command. Because of this, it started a rejuvenation of sorts in optimization theory, right? Okay, because this is a very simple quadratic program. What is the big deal? Of course, so, okay, one of the things is, maybe that's where the mind block is. See, most of the challenges your theory community engages in making really hard problems, NP hard problems to polynomial time. And that's where a lot of good things happen, right? But to attack data science related problems, even n-cube is bad. Like n-cube is as good as NP hard kind of thing. That's the mindset you have to take. And that's where the challenge is. So n-cube 10 square kind of thing, or n, that's the thing we would like to, and that's where the opportunity is, I guess. So now, this is great, right? Now, okay, so why am I showing this may not be necessary, but probably the one way to do that is to show this thing that you can write a dual for this. And the dual, if you see the variables are now scales, and number of variables becomes equal to number of constraints, n. And n is a large one. Huh? N is quite large, right? That is the thing. So now, it's a very nice, interesting geometric picture of SVMs. So what is it? That assume in 2-dimension, there are these diamonds and these pluses. And so basically the pluses and diamonds are lying on two sides, just though you don't know. Now the thing is, one way to do that is, you can draw two lines. On one side lies the crosses, on the side diamonds. Once you have the line, you give me any unseen point, and I will say which side of the line it lies, and I'll tell you that's your decision function, the fx. That is the idea, right? Now the way it is proposed, the thing is that if you knew these 3 points per se, you get the solution. That comes from optimality, KKT conditions, all kinds of things, right? So that means I don't need to figure out the whole data points, whole set of n data points. If I can guess these 3, I'm done. No question how, right? So now that being said, so as I said, alluded to this setup now, that probably there are very good solvers where n is low. So let's assume the following. There are many attacks on this problem and all. That's one of the things I was thinking in 2005-06, that was the peak of the SVM research and all that, right? So now I have access to a small solver. Small in the sense it can solve for small n. Okay, I can call it as many times as you want. Can you solve that problem? Okay. And now, okay, a simple thing, if you have money, what you'll do is, okay, who cares? Paralyze it. I don't have money. Machine is fixed. I don't want to paralyze it. What can I do? I have a small solver, one machine. The paralyzing not allowed, right? So here, then the interesting thing is, theory community has done a lot, especially in solving large linear programs, right? Especially, so now one of the things is of interest is, suppose D is low, that A is so this is a problem in D variables, and N is a number of constraints, right? Now think about the case where N is much, much larger than D, right? And now, so there has been a lot of good research on this, especially randomized algorithms, right? So here is one, when I learned about it, this looks absolutely brilliant. But for you guys, look quite, so it's basically this Clarkson's result on randomized algorithms. So, so those of you who are not aware of this, so what he suggests is the following. Remember, n is much, much larger than d. I have a small solver. That is, I can solve for small m and small d, right? Now, let's say m is like 6d squared. What he suggests is the following. You take your solver, which can solve for m constraints and d variables. M is like 6d squared. Okay, you sample from your constraint, solve it. Okay, then what do you do? Because the problem is convex and all that, you have to, the constraints must satisfy the KKT conditions. If you solve the KKT conditions, I'm done. So what you do is you figure out the KKT violators, that among the things you're not sampled, which of the constraints are not satisfied. You'll find plenty will not satisfy, right? Then what you do is you just double the weight of sampling. Do it again. Do it again, do it again, do it again. And you can show, with probability 1, it will converge. This is an amazing piece of result, right? And now, if you think more clearly, those of you who are aware of these, see at optimality, when the duality comes, X, basically there are only D constraints is what you need at optimality. But just that you don't know them, which of the D constraints. Because it's a D-dimension vector. I need D independent vectors, right? To describe a solution. And that's what he hunts for. And that is why he initially poses this, that, this since D square, right? That's where D, right? Now, this can be generalized to what is known as LP type problems, right? Right. So you can think like this. This is on a set. What is a set of constraints, right? Now, on the set of constraints, I have a objective function. Now, so long as objective functions have two property called monotonicity and locality, we can discuss that. It can be generically applied. Nothing to do with LP per se. So this is an amazing thing I learned. Good question. Okay. So it's okay if I won't go through all the slides. It's fine. So we'll do that. So locality is okay. So now let us say S be the set. What is that set of constraints, right? And phi S is basically C, C transpose X minimize X. Now your constraint set is only this, not the full thing, right? S is a subset of this, right? Now, so locality would be so locality is if phi S monotonic. Okay, so if let's say S is less than T, right? So phi S is less than phi T is monotonicity. Okay. Now, if phi S, okay, so now the locality is defined in another subset of T. Minimum of the. So if you add more constraints, that's the thing, right? Right? And now, okay. So this other thing is that, so now if so something with violators, right? They are defined through violators. Violators is one way of defining violators is that, see, you solve this problem through S, right? Now the number of violators in the KKT set, right? Right? Now, if phi T equal to phi S, where T is again subset of S. This has happened. T subset of S, phi T equal to phi S, right? Then the violators of this is going to be the same. The violators of these two is going to be same. That is, if phi T equal to phi S, right? T is a subset of S, by the way. And the objective function value is same. That means, though I solved for T, but none of the things in that S violates T. This is some one way of seeing the locality, right? So that means, see the whole thing. So these insights have come from the thing called Welzel and Gartner. They looked at this and then defined this. So the main thing is that this is those of you who don't know Clarkson, you should, I request you to look this up. It's amazing. While his other idea, Porser, is very famous, but I think this is equally important in this sense, right? And now this has far bigger applicability than linear programming, because I can think of set functions now. So one of the things I was bringing this talk to this audience is that maybe like, are there other developments there? This is like 30 years ago we are talking about. I'm sure a lot of good things have happened that I don't know. So this is one of these, right? Locality monotonicity will. Huh? There is a hyperplane with a sufficient gap that completely separates two things, or we are looking for a T-square. We are trying to find the best. Even the SVM part. Yeah, in the SVM. Yeah. So SVM part, let's assume the following, that this picture holds. That there is a hyperplane with a gap. This picture holds, right? We can make it more complicated, but this is the idea, right? Now the question is, all this nice theory, right? Can it impact that problem? Say it again. Yeah, the various program. And if it's feasible. Yeah. It's feasible. That is that the constraints, sometimes the linear program can be such that it may not have a feasible solution. The set is empty. Suppose I don't think Clarkson result applies there. The set, there is at least one feasible point for which the problem can be solved. You can put as many constraints as you like. Okay, but so long as the problem constraints are not conflicting, so that the problem becomes infeasible, then this result will apply. Okay. Well, those are all, yeah. So okay, so we will talk about those things, but But the main interesting thing, as you can see, is, okay, let's for now, we can discuss all of that. But main thing I want to take away the following point, right? Here's a tool somebody is giving us to solve a small problem, right? Called many times, and probably showing that you can solve the bigger problem. And where, of course, the fact is linear program and things like that has to be exploited. And all this plays out in a nice way, right? You know, yeah. So, okay. Now here, the fact is that, you know, so if you look at the dual problem, right? The duality, you know, now let's go back to SVM problem, right? W is equal to then linear combinations of this yi, xi. So alpha is the things I do not know, right? Now the question is, what is this delta? The D, as you said. Now, what they're saying, this also I don't have full understanding yet. Maybe I should do another PhD in theory, sign up under Kavita maybe. So the fact is that the D, right, dimension, that for linear programming, D variables, I need D, D-dimensional space, I need D independent vectors, right? Similarly, the notion is delta, the combinatorial dimension of the problem. So we can generalize to arbitrary linear programs, and this is the combinatorial dimension is delta. Now, for a given problem, I do not know what delta is. You know, that still one has to reflect on it. But for example, in the problem which you had the parallel lines thing, right? Basically, you need in a D dimension, you need D+1 points, right? I can draw two parallel lines, right? I don't need any fancy theory. I just need to. That's what I mentioned in the picture, right? 2 dimension, 3 points enough. Which 3 points? That I don't. But I know the 3 points if I get, I can solve the problem. So so delta was D+1. Okay. So at that point, okay. So delta is D+1, great. 2007. So I said, now in ML community, you get at that point, you get bragging rights. So I had done something fancy. At that point, this SVM, oh, fancy, right? D is like a million. Oh, sorry, not million. No, sorry. D is like 20,000. Then you get your bragging rights. D is 20,000, 6D squared. I'm already kidding. Doesn't work. Okay. Now, the observation you made, are the things separated, right? So that means so now here's one more interesting tool, you know, and the way I got exposed to was again from theory community, this famous result, Johnson-Lin stress. So here's the statement. Many of you have seen this, but in a nutshell, you know, it is something like this: that if you have m points in d dimensions, right, and you want to preserve their distances, I can just split them to log m dimensional space. Right? Now what I can do is you have this n is quite large, right? So basically I can now use a projecting term to log n dimensional space, random. If they're far apart, you know, this will distort it slightly, but probably the separation will still remain. But then what I get is my delta now becomes, instead of D+1, becomes log n. And now I can use Clarkson log n square, right? And I can use a dual to iterate over these things, right? And that is the whole agenda of this, right? You know? So basically, you know, that's where our Clarkson kind of things, right? I mean, so this is an amazing piece of result, right? And we just wrote. So this was done with my colleague Ramesh Hariharan and Krishi. Now, this is one of the takeaways I wanted to ask. Now, I just came across by accident. One day I was thinking about how do I solve this in a small things, and some of the randomized algorithms. I picked up Motwani Raghavan's book, and then it happened. Then asked Ramesh and things like that. So maybe you guys, what else are you hiding for this kind of problems? Right? There's a huge impact in today's, you know, today modern machine learning. I have to shuffle through lots of data, training and all that. I'm sure there are many such kind of technology will definitely help, right? Okay, so this is one setup, right? Now the second. Now, shifting gears, we have not come to the main agenda yet. I don't have to. I think I like this discussion, right? Okay. So, so this is changing gears. So let us say G is a graph, standard simple graph, right? And now that equation, all of you know, right? Independent set, chromatic number of the complement set, and in the middle is the famous theta function. I don't know why they use the hard theta notation, complicated, theta g. Okay, this is a very famous inequality invented by Laszlo Lovász, right? Now, the interesting point is, at the two ends, there is NP hard quantities. In the middle, there is something which is polynomially computable. Essentially, this is also an instance of what is called a semi-definite program, SDP. Okay. And now, so alpha G, right? That is the independent set, right? Right? Correct number. Okay, yeah. Equation is right, no? No, this is not my. I feel nervous about doing this kind of talks. The ML community don't even know all these things. Kai would say, "Oh, indicator function." Yeah, sorry, there's no ML guys here. Right. Okay. So now the interesting thing is, we showed you one instance of the SVM dual. Now one can think of more instead of x's, you can use run an SVM on a very complicated space, like x to another mapping phi of x, and that when encoded is a kernel function, right? K of xi comma xj is this. I think I had a income. Anyway, so yeah, kxi xj is one instance of xi is this, right? So kxi is like a dot product and all. Now the question is, if you give me a problem like this, some result after lots of good research, we can solve it in linear time, linear in data, n square is my data, right? Yeah. So open source software exists and things like that. Okay, now here is interesting thing. I flashed a slide on Lovász, went back to this source vector machine, right? Now the question is, see, now for a given k, I can solve this, right? So omega k is like this objective function value. Give me a k, and I can solve, I can evaluate omega k through like this, right? Okay. Now here is our result. Actually, you can view the theta function as if learning a special kernel function. Where the kernel is, remember those of you know the theta constraints is, so here are the constraints on the graph, right? If G, the edge set of G is E, now if it is not in the edge set, right, your Ij is not in the edge set, you set the kernel to be 0. Okay? And now Kii is equal to 1. So the diagonal entries of the kernel matrix is 1. You give me a graph, right? Graph is a vertex on n. There are n vertices, right? Now, where there's no edge, you just put kernel matrix 0. Other entries can do whatever they like. Okay. Now you're allowed to put whatever they like, provided the kernel matrix is positive definite. Now, if you solve an SVM and figure out the one which is the minimum value of omega k, it's nothing but the theta function. Okay. Okay. Fine. Interesting connection, but what can it do? 2 points. ML community, for whatever reasons, know how to solve omega k very, very well. This kind of problems very, very well, because kernel learning is a thing in this. So now it sets up an interesting, collaboration opportunity that can I use those tools to solve for theta? Now here's the thing. This is why can solve for theta? Right? Theta, polynomial time and all that, but SDP by n to the power 6 is as good as not solvable. I give a large graph, you probably won't. Of course, so now having said that, this is like little old, and a lot of good things have happened. Now I'm sure a lot of powerful solvers also appeared. Okay. Now, so now, as you said in the beginning of the talk, right? I said that, like, for example, if you're not happy with the polynomial time statement, you want to say, look, how quickly can I solve it? Suppose you are interested in that kind of setup. Now you see there is a almost free K available. This is done by Lush and Shriver. So what they said that if you use K equal to A by rho plus I. So rho is the minimum eigenvalue of the adjacency matrix of the thing. you'll see they have the same property as what you wrote down here. So this is one of the feasible sets, right? Theta is minimum over this. So this will be a little higher. But the interesting thing is I can do it in n squared time. It's almost free. Rho is the minimum eigenvalue of A. So max n cube. Right? And you can, and since I'm only asking for the last one, I can do n squared also. Right? This is almost free. Now, the interesting thing is, if you can show this is tight. Are there graphs? Lots of graphs are there. Right? That means I can, on certain graphs, I can solve it much easily, no? Okay, so that's a different discussion. But here is one thing I wanted to show. We should have done with some pictures and all that, but so basically, you take a graph, Erdős-Thöny graph, G and half, on which you plant a click on the first k things. Okay, now you invert it, you complement it. So then I will have a independent set of size k, this is G bar, right? Now, if k is pretty large enough, right, C root n kind of thing, you could show that the theta function is equal to the k. The planted click problem is to find the click, right? So now now using this, Feige and Kraus-Gommer gave a algorithm to figure out where the planted click is. But to do that, they have to solve theta g. Theta g is n to the power 6. Right? And you can see why is interest in this? Because if I can do planted click is more like an abstraction. That means the more interesting thing is, can you find dense subgraphs? And that's a lot of applications, right? So I can solve that kind of problem. That's why the people have created these abstractions, right? Okay. Now here is our interesting result, because I've already I've shown you this thing, right? So we can show you that if for example, if k, is like in this regime, right? C root n, you take your SVM approach because of the results which I showed you. We can also confirm first principles. We can show you omega k is equal to this, right? That is, if now as you put t large and large enough, right? You see omega k and theta g roughly starts matching. And what is omega k now? Solving an SVM. Now I can solve a planted click problem by solving an SVM. And is it a theoretical thing? Okay. In the sense that, okay, good, but can you show me a validation? So validation is, I'll welcome you to read this paper. This is with Devdutt. This is, I was in Sweden for a year with Devdutt. Probably many of you know Devdutt. So with him, so you can look at this and see the experimenting just works like a charm. And the charm is that, and first of all, it is easy to solve. I don't need any SDP and all that. And so far as k equal to 2 root n and things like that, it works. But I guess the real challenge as a planted click problem is probably that, okay, can you do in below root n? That part, we're not saying anything. It's merely a computational exercise, right? Now, another thing is of very great interest in today's machine learning community, especially in AI. You hear this word called representation learning. Now, for me, the way I learned about this theta and all that when I went about it, and frankly speaking, several tutorials I read, I didn't understand anything. So the way I understood this and reached there is that I think most tutorials focus on theta as a black box that gives you a number. But I think there's more richness to how it comes up with a number. It represents each graph, each vertex of a graph by a vector, which they call as orthogonal labeling. There's representation, right? And I think that has a lot to offer to today's AI community, especially people think of graph neural networks and things like that. Okay, and that's where also I learned about it. This is the way we went about it anyway. So interestingly, so one of the things was that suppose I give you multiple graphs on the same vertex set, that set just changes. Now, can you figure out a common dense subgraph? There's lots of uses. For example, if we start inducing graphs based on our book taste, on our food taste, on our music taste, that set keeps changing in the same room, right? But are there something common? And now, so we pose this problem, and kernel learning has a very interesting, it generates a very interesting heuristic and solve things very quickly. But this problem, I think, then theory guy people picked it up, and they have done some very interesting work on this. So this I'm flashing, as I said, that these are two instances where I thought there's a good collaboration between CS theory and machine learning and all that. But looks a little dated though, but I think these ideas still have their place in today's day and age. Or yeah, graphs are huge. The theta is okay. So theta, see theta function is the way it was crafted is the what is it, the Shannon capacity of a graph. It came from information theory and was used to prove chromatic number and clique number or independent set, depending on what you have to take, right? So unfortunately, so this means this is only known in these two communities at max. In information theory community also, many of them don't know. So the Shannon capacity is not very useful in many ways, right? So theta has not, I mean, I think everybody should know this in a sense that MLs definitely know this, but I don't think that they're aware of this. But I strongly believe, but now you don't need me to tell this, graphs are everywhere. Now people are modeling everything like graphs, interconnection and all that, right? So the impact of theta on this is, I'm not seeing. But this is just telling us that, you know, it can be both ways, right? So one can take these theta functions, more than theta function, look at the labeling and can you come up with interesting conclusions on large scale graph problem for the commodity detection and all that, right? Yeah. So large graphs are pretty common. Theta, it's your job to make theta popular and tell ML guys, what are you doing? These are such nice theory, interesting things to, right? Okay, so now, okay, now let's come back to the agenda, but do we have to? 10:13 already, great. So, okay, I have not started the agenda, 10:13, 45 minutes already gone, right? So now how many, Raghuvan said 50 minutes. Good, this is one talk, agenda. Okay, he's the boss. Okay, then I think what I'll do is, okay, I'll not, okay, so maybe what I'll do is I'll take 5 minutes on the latent variable. I had a lot of slides, but I'll take 5 minutes to tell you a problem. And then we go to the quantum EM, another 5 minutes, right? And then we can have questions. Okay. So I'm sorry, I thought the first thing we'll do to show the interconnection between, you know, theory and ML, and that will be of interest. So now, okay. So latent variable models, you know, so what are latent variable models? So latent variable models are something like, it defines something like a probability law between something is observed, something is unobserved, right? So today generative AI, essentially this. So that's how you define a generative process of the observables. And of course, there are unobservables, but it generates, you know, things like what you see. Now, the main thing is to find out the parameters of such a model, let's say. And often, most of the interesting cases, it turns out to be intractable. Now, the question is, in such a setting, can you can you, under certain conditions, let's say, can you at least solve such problems, right? So now, let me motivate you a small example. So imagine there is a book load there, right? And you're a librarian. Somebody dumps some books on you. These are like websites for it. And a company has to serve, you ask some questions. So you go to a librarian and say, give me a book on, you know, what are restaurants near TFR? Where can I find this information? Right? And if it's like this, it's very difficult to find things out, right? Probably you need index and things like that. So now keeping this in mind, something called topic models were invented. Basically, this can, if you have the topic models, means if you have the topics, you can index those large collection of websites. So idea is that can discover hidden themes in document collections, right? Once you have the themes, you can use many things, you know, for example, labeling. Now, it was a machine learning challenges because most of the machine learning area we see huge development is what is called a supervised learning. That is, I have an X and I have a Y. I have an image and say a dog. Image is a cat. Now it gives me a target. Here, where is the target? There's no target. Somebody dumps on me a collection of like documents and say, what are the themes? Okay, so now this has some history, but does not get there. So now what could be a theme like, right? So what are the topics? So now think like this, you have to very quickly come up with the understanding that this document is about what. So suppose I say the document contains the following 5 words: run, inning, hit, season, game. What can this document be? It's something about cricket or baseball, you will say something like that, right? For example, like cup, minute, add, tea, tablespoon, oil. This is like cooking. I don't need to understand the grammar of it. I don't need to understand all kinds of other linguistic nuances about the document. Right? So this is something like topics. So topics are essentially probability distribution over words, right? And now, so this is what is called as a graphical model, and this is probably one of the most, and that's where this emerged, David's work. So basically, we have W is a set of words, and there are n words in a document, and so basically each topic is a distribution of words in a vocabulary, right? Now, the way you generate a document is you first sample a topic assignment. So what is it? So now I have these 4 topics which I showed you, right? So I say, I know there are only 4 topics. Suppose I know this. What I do is first word, what is this topic? I pick from a distribution. Once I have this distribution, then I draw a word from that topic, right? This is a word sport. Okay, so draw a word from the distribution, right? And things like that, right? So obviously it doesn't say much. There is things in 5 minutes. So obviously it's a mess because I have to find out the parameters. You give me a corpus, I have to learn the distribution, right? It becomes a mess. So all kinds of complicated equations. And doesn't say much that you can easily show it's NP hard, right? By inference, I mean figuring out this unknown parameters, right? Now, EM algorithm is used as an approximation for this setup, and it gives some good approximations, and it's pretty good actually when it emerged. So now here is actual working codes example which David shows that it can mark out regions from like these are like science documents, and you can read this aloud. It works pretty well. It can mark out things like that, right? Now, so now here, so where is the intersection between compression theory? Okay. Now, if M is the collection of topics, what are topics? Distributions over words. So now there is a D words in a vocabulary, and there are K topics. I need to figure out the D cross K matrix, where each column is like a probability distribution, a PMF. Right? So now A is my corpus. What is my corpus? Now I collect each document. I say, oh, this word appears this many times. This word appeared that many times. Another vector of D dimension. You give me this matrix A. That's my corpus. You ask me to figure out M. Standard procedure, maximum likelihood, you do. Now, as it is showing, that is obviously you'll end up this is NP hard. Finding out, right? Okay, but you can approximate it. We showed one approximation EM algorithm and things like that, right? Now, so here comes a very interesting perspective. Okay, for this problem. So think like, so where is that? Okay, you have the same topics. A document can have multiple topics, right? Now, let's say, but so let's think of a document as coming from a composite topic. I mix up all the topics. First word is on topic, second is on topic, and things like that. And now what you do is from the composite topic, you draw M words. And now you catch this, that your collection of topics from this W vector, right? Okay. Now this comes from Sanjeev Arora. Nothing less than a breakthrough, I would say, the way of thinking. This is a Fox paper, right? Okay. Now this shows that under that assumption that to make a, of course, you can't get away from the NP hardness. So to make some assumptions, he assumes, suppose there is one word. So every time, basically the word, oil will not come in sports, will not come in computers, will not come in some other. That is, so that moment the word oil appears, you know it is this topic. Right? This is called separability assumption. So assume for each topic there's one particular word which immediately occurs, means that that topic is. Now using that, they ingeniously come up with this kind of result that you can learn M from finite number of samples in polynomial time, where S is given something like this, right? Now, okay. Now what I'm going to say is more like nitpicking, but this is the great word, right? Now the question is obviously, so now here, S, what is S? The number of documents I need from which it is created, right? You need minimum so many documents, right? And that's what they say, S is something like this. Now, P0 is basically the occurrence of those separable words. Now, you see P0 to the power 6 in denominator. But my vocabulary is something like what? Minimum 10,000 words. So what is P0 now? Even if P0 to be 0.1 or 0.01, this blows up in your face, right? I mean, so basically there may be something they are not doing exactly right, but I think the principle is probably right. Now we make, so when you say we, this is me and Ravi Kannan. So Ravi was visiting IISC at that point in 2012, and he was asking me, because I had done some other work on topic models thing. Then he was asking me, this paper came out, what are the things? So, and he was explaining me this paper. So I said that, look, they're not using the fact that where is actual data involved. There's one thing to write equal to MW, that's great. But now the experience in working with actual data is not there. In actual data, what happens is a topic can have multiple themes, right? But any topic has one dominant theme. Right? By and large, it's about sports. By and large, it's about, see, that they're not catching. Okay. And now one more thing I wanted to highlight is that this thing called going beyond SB. There's a history involved here. So this thing emerged from what is known as latent semantic indexing in 1990s. There, the understanding was each document has only one topic. And LSI, there was used to explain LSI under that model. And LSI initially does what it does SVD of the data and solves the problem. That is why they said that SVD, because this is now a different model which says a document can have multiple themes, multiple topics. So obviously you have to do beyond SVD. That is the thing, right? Now, when I was Ravi was visiting, so I was telling him that, look, you run experiment, this is what will happen. Remember, SVD was what? One topic, right? I said, no, it's okay, but one dominant topic. And, so long story short, basically a simple algorithm like this, right? What you do is you compute an SVD, I'm hiding something here, so don't run SVD not on the raw data, but you do some thresholding and run SVD, then use a cluster using k-means, and this will recover the dominant topics. Once I get the dominant topics, with the assumption that each topic, there is at least the corpus is such that there are some few documents which are purely about sports, which are purely about cooking. These assumptions, our algorithm definitely does, right? So now, so we call thresholded SVD, right? TSVD. So here, as I said, I'm hiding something. So you see here, our thing becomes P0 square, right? This was P0 to the power 6. And of course, this P0 is also not on a single word. We say a group of words must come together. Doesn't have to be oil, but oil, salt, sugar means cooking. So P0 is distributed more among a group of, right? They're more realistic. But anyway, so now right? But essentially, we went about this proof using Ravi's own work with Amit Kumar. About the data. So this is an example where you see, like we had this problem of topic models, information retrieval, this and that. Now Sanjeev Arora and group came with amazing simplification of this P equal to MW and all, open the eyes. Okay. Now, maybe I'll not do the quantum stuff. Just lack of time. Maybe I'll not do the quantum stuff. I want to show some pictures of this. Okay. So now, the thing, right? Topic models are like we did, right? Then we're just playing with this model. What is this thing? So essentially, there is actually, if you look very carefully, there's high dimensional geometry looking at your face. So here are some instances of these two work. And this, I think, is of interest to theorists per se. Forget the application of it. You know, let me illustrate that. So first, if you go back to this model, our model was MW, right? MW is P. Now from P, I generate M words. That's what I see. So you can view this as following, you know, that as if I'd taken the vector P and perturbed it. Random sampling, I see this, right? I just perturbed it, right? So it becomes a very nice geometric problem. And just to see, okay, here is, yeah. So here is the thing now. I want to show this because I did took some time to develop this. Yeah. So let's say there are 3 topics in 2 dimensions, right? So MW means what? W, as you can see, if you don't paying attention, W is like the sum of W is equal to 1, W is a positive basically in the convex hull, right? So now, so for example, if a document is very near M1, right? So this is your P. And now when you draw samples from it, probably you'll get a green star, which is pretty close. It may or may not be in the convex hull. Okay. Now, here, what is the learning problem now? Learning problem is, I give you the greens. Can you figure out the pinks? This is data you see, right? I give you the greens, you figure out. And the green points may be in the hull, may not be in the hull. Right? As simple, right? I hope the problem is clear. Now, what I can very simply do is, fine, okay. Let me take a convex hull of the greens. Greens is what I see, right? I don't see the pink. Okay. So now, you see, so now the exit techniques, the volume will be well approximated, but I don't want the volume. I want the extreme points. And so a simple thing like, you know, just in convex hull of the data will not work. Right? So this is what I call latent K polytope problem. Latent, the polytope is latent to you. Right? Now, how do you solve this? Okay. So here is Ravi's magic. So basically, so now here is a way to understand it at some sufficiency conditions. Now here's the interesting thing, we'll take this. So there are 3 things. You have this M, you have this A, and this T, right? So for M, as you can see, vertices must be reasonably far apart. Otherwise, there's no hope. Okay. Then on A, right? Now, obviously, if A cannot be too far from P, the PI say, if too far, nothing, everything is anyway lost, right? Now, one extreme end, I can say that each AI lies very close to PI, then it's trivial. Not trivial, I mean, probably it's not catching real world sense. So on an average, Ds and Ps are close. On an average, but some data points can be quite far. That's very interesting, right? So that's the spectrally bounded perturbation, right? And lastly, the point we are trying to make, right? There are some documents which are pure, right? To speak to that, we said that, okay, there can be many points, but there should be some small fraction of points which are close to each of the pinks. Same AP, right? So once you have this, and then there is a polynomial time algorithm where you can recover the M's, right? And the complexity is more like the number of non-zero elements in it, right? So immediately I applies to wide class of models. For example, topic models is one. Now, you also heard of something called non-negative matrix factorization. These are all cousins. If you can solve one, you can solve one. So all this applies to these things, right? Okay, it's 10:30 now. I'm sorry. No, I can speak for another hour. You know, you guys are good listeners, but I think I've already overshot my time, I guess. Yeah, so this is all some of these things, but maybe just to show, so okay, so we gave you one, so here's an instance ML giving you one problem to theory community, latent K polytope problem. Go learn about it. Like, what can I do? Now, latest, right? So the way we're thinking is, So many of you know this interesting problem of separating hyperplane theorem. What is it? I give you a convex set, I give you a point. Now, if the point is not in the set, you can draw a line. This is important is because this is the cornerstone of most modern day optimization. Right? Now, here is one thing while you're developing this, because see, a lot of random things are involved in this. So for the polytope case, this is, so now think like K is a polytope, right? Now, obviously, separating hyperplane theorem is something like this, right? Now, we were asking that can a random you separate a polytope from a point? I think it is actually, obviously, the face of it is cannot. But the condition is not too, it's not too bad. If number of vertices is quite low, one can have a result like this. So this is called random separating hyperplane. But this only works not for a generic convex set, but a polytope with K number of vertices. Now, these can be used leverage to solve the problem which I mentioned before. Now, I strongly think this is far more applications than we can dream about, right? And I guess this is the right community. I think every whole country knows the best students in CS theory ends up here, not to IISC. So I'm sure they will take this quite far. Okay, so I'm sorry I'm running out of time. Maybe quantum some other day. So thanks for listening. Yeah. Yeah, happy to take any questions if you have. I'm sorry I couldn't go through other things, but that's fine. Oh, you're welcome. Sure. Yeah, is there any questions?
The separating hyperplane is not perfect.
Mhm.
The data point the is not a hyperplane that clearly separates the stars from the flutter. But there are a few outliers. But suppose all we want is to find the hyperplane that minimizes the error in the set. To the standard SPM algorithms also work in both.
Yes, it does. That's the main thing. That's a very ideal case. Right. So now one can frame this as an optimization perspective, and one can do something like that. So the Clarkson algorithm that way is okay. Say the thing, and let's see if you can clean this up. Way we solve the same. See, unless we solve that, nobody's going to care about it, right? So now what we did was assume the problem is very well separated, nearly well separated, right? So what the idea is that you throw away a small group of points, the problem becomes separate. And you run Clarkson on that separated data set. And this is the way we went about thinking ourselves. But it worked well, and the worked well is because of this set function. So nobody said phi x, phi of s, right? The set function there doesn't have to be perfect separability, right? Okay. No, that's the thing. I don't know this. That is the thing. If you know this, the problem is solved, right? And that is the essential idea. Okay. Okay. So, no, why is it here? No reason. Okay. This is that I'm sorry. This is that thing, even the Scarlett Johansson kind of idea. That now, so now there's no, at this point, there are no good answers to this. We are grappling with, right? How do you formulate the problem even? How do you solve this problem, right? So I think is that, can you forget a class? I'll forget all the cats. I forget all the dogs. That's the best you can come up with. Unlearning. Now the question unlearning problem is this, that, right? Unlearning. So what is the unlearning problem? Since it's there, you have learned a model with all cats, dogs, everything, right? Now somebody said, no, you have to forget all the cats. What can I do? So what is forgetting mean? That means, can you prove to me, do whatever you want, that the model, if trained without cats data, is this model? A simple thing, if this is the formulation, start. And I already saw electricity bill you already saw, right? So now retraining from scratch is not an option. So what changes can I do to the model? Where I can convince you, it has forgotten. And convincing is also, see, this has become serious judicial issues now. So here I think algorithms and things like that will have a huge role to play in the coming day, right? Class-wise unlearning is a very, this is not basically the best formulation problem. Best formulation that I want to forget this data point. I want to forget Chiru came and gave her talk. All traces erased, right? So that is, by that I shouldn't forget all the speakers. Class unlearning is all the speakers. Yeah, anyway. Okay, so thanks again for listening. Thank you very much. Thank you very much.
We have a 25-minute break and then we have. You believe that? Wow.